Hello friends, I welcome you all to the course on integral equations, calculus of variations and their applications. We shall first discuss the definitions and then we shall discuss the classification of linear integral equations. Let us see what do we mean by an integral equation. An integral equation is an equation in which an unknown function appears under an integral sign. The integral equations play an important role in the study of initial and boundary value problems. Such problems occur in applied mathematics, mechanics and mathematical physics. The physical problems, namely radiation transfer problem and neutron diffusion problem, lead us to integral equations. In the present course, we shall only deal with those integral equations in which linear functions of the unknown function are involved. So, that means we shall be dealing with only the linear integral equations. Now, let us see how the integral equations actually the study of integral equations began. Abel in 1826 worked on a problem in mechanics which led us to an integral equation. So, let us discuss the Abel's problem. Let us consider a smooth curve in a vertical plane xi eta. Let us consider a smooth curve in a vertical plane xi eta. Suppose a particle starts from rest from any point P with ordinate x. Let us say the ordinate of the point P on the curve be x under the influence of gravity along the curve, and let t be the time taken by the particle from P to the lowest point r on the xi axis, and let us assume that t is a function of x, say f1x, where f1x is a given function. The absolute velocity of the particle at a point q on the curve the absolute velocity of the particle at a point p on the curve whose ordinate is eta. Let us say the ordinate of q point be eta, then the vertical height pq will be x minus eta. So, the absolute velocity of the particle at the point q will then be given by b equal to under root 2gh, that is 2g times x minus eta. Now, let us say beta be the angle of inclination of the tangent to the curve at the point q, then with the y axis, then what do we have? The velocity along the eta axis d eta by dt will be minus under root 2g x minus eta into sin beta. Now, we can also write this equation d eta by dt minus under root 2g x minus eta into sin beta as dt equal to minus d eta over sin beta under root 2g x minus eta. Now, let us assume that 1 over sin beta be equal to phi eta, then we can write under root 2g dt equal to minus phi eta d eta over under root x minus eta, and integrating this equation, let us see, we have under root 2g dt equal to minus phi eta d eta divided by under root x minus eta. Now, we have assumed that t is the time taken by the particle to slide from the point P to the point R on the xi axis, the lowest point. So, we have to integrate from P to R. From P to R, when we integrate from P to R, we get this. Okay. Now from P to R the time taken is T, so under root 2G into T is equal to, now the because of this negative sign we can also write it from R to P, so we shall have under integral R to P phi eta d eta over under root x minus eta. Now the ordinate of the point R is 0 and the ordinate at the point P is x, so we have integral 0 to x phi eta d eta divided by under root x minus eta. So we get under root t times under root 2g equal to integral 0 to x phi eta d eta divided by under root x minus eta. Now t we have assumed to be equal to f1x, so we get under root 2g f1x equal to integral 0 to x phi eta d eta over under root x minus eta. Let us assume that under root 2g f1x is another function, say phi fx. Okay. So fx we can write as integral 0 to x phi eta d eta over under root x minus eta, and since f1x is a known function, so fx equal to f1x into root 2g is also known, and phi eta is the unknown function. Now so from the equation fx equal to integral 0 to x phi eta d eta over under root x minus eta. We notice that fx is the known function while phi eta is an unknown function. So it is an integral equation, and we shall see later on when we discuss the classification of integral equations, we shall see that this is a Volterra integral equation of first kind. So after finding this phi eta, the unknown function phi eta, we can write the equation of the curve in the parametric form. We have phi eta equal to 1 over sin beta. So phi eta equal to we have assumed phi eta to be equal to 1 over sin beta. So we can say that eta is a function of beta, and now beta is the angle made by the tangent at the point Q with the xi axis. So we can say that d eta over d xi is equal to tan beta, and r we can say that d eta from the equation eta equal to phi beta, we can say that d eta is phi dash beta d beta. So we can write d phi dash beta d beta over d xi equal to tan beta. R integrating this equation, we shall be getting xi equal to integral of phi dash beta d beta upon tan beta. Now this will be another function of beta which we can write as capital phi 1 beta. So we can get, thus we get the required curve, the path followed by the particle we can write in the parametric form, which is xi equal to phi 1 beta and eta equal to phi beta. Now this, so Abel's problem, which where we are finding the curve followed by the particle can be expressed in the standard form, where if you define 1 over under root x minus t, we can write it as also as fx equal to integral 0 to x phi t dt in the parameter t, let us write. So under root x minus eta, x minus t, then this is nothing but integral 0 to x kxt into phi t dt, where kxt is equal to 1 over under root x minus t. So kxt is known to us, and fx is also known to us and phi x is an unknown function. So, we get a Volterra integral equation of the first kind where kxt and fx are known and phi x is an unknown function. So, this is how the integral equations occurred while solving problem in mechanics. Now, let us discuss the most general linear integral equation. The most general linear integral equation is gx into by x equal to fx plus lambda times integral a to b kxt by t dt, where fx, gx and kxt are known functions of x and t, while by x is to be determined. So, by x is an unknown function. Lambda here is a non-zero real or complex parameter. The function kxt which occurs inside the integral is called the kernel of the integral equation. Now, if it so happens that the limits of integration, in the limits of integration a is a constant while b is equal to x. So, then the integral equation will be called as Volterra integral equation. If both the limits of integration a and b are constants, then the equation will be called as Fredholm integral equation. So, there are two kinds of integral equations, one is Volterra integral equation, another one is Fredholm integral equation. In the case of Volterra integral equation, the lower limit is constant while the upper limit is a variable x, and in the case of Fredholm integral equation, both the limits of integration are constants. Now we will discuss the various kinds of Volterra integral equation. So, Volterra, a linear integral equation of the form gx by x equal to fx plus lambda a to x kxt by t is called as a Volterra integral equation of the third kind. Now, in particular, suppose gx is equal to 0, gx is identically 0, that is gx is 0 over the domain of g, then the equation the equation 2 will take the form fx plus lambda integral a to x kxt by t dt equal to 0. Such an equation is called as the Volterra integral equation of the first kind. Fx equal to fx plus lambda, you can also write it as fx equal to minus lambda integral a to x kxt by t dt. The Abel problem is of this type, and where you can say that lambda is equal to minus 1. So, this is a Volterra integral equation of the first kind. Now, on the other hand, if gx is equal to 1, if gx is equal to 1 here, then we will get by x equal to fx plus lambda integral a to x kxt by t dt. Such an equation is called as Volterra integral equation of the second kind. If fx is identically 0, fx is 0 for all values of x in the domain of f, then what we will get, by x equal to lambda integral a to x kxt by t dt. Such an equation is called as homogeneous Volterra integral equation of the second kind. Okay. Now, there occur singular integral equations also in the in literature. A linear integral equation will be called a singular integral equation when one or both the limits of integration a and b are infinite, or when the kernel kxt becomes infinite over the range of integration. For example, let us consider by x equal to fx plus lambda integral over minus infinity to infinity e to the power minus mod of x minus t by t dt. Here you can see that both the limits of integration are infinite. So, it is a singular integral equation, and in this case the other example we can consider where the limits of integration are finite 0 and x, but the integrand 1 over x minus t to the power alpha, okay, this becomes infinite over the range of integration. Kernel 1 over x minus t to the power alpha becomes infinite when t becomes equal to x. So, fx equal to integral 0 to x 1 over x minus t to the power alpha by t dt, where alpha is between 0 and 1, are both singular integral equations. So, now let us discuss Lebanese rule of differentiation under integral sign. We shall need this result when we discuss the when we convert the integral equations into differential equations. So, let us say let fxt and its partial derivative with respect to x be continuous functions of both x and t, and the first order derivatives of gx and hx are continuous functions. Then d over dx of integral gx to hx fxt dt is equal to integral gx to hx partial derivative of fxt with respect to x into dt and then fx hx. So, in fxt we put t as hx, the upper limit, and differentiate the upper limit with respect to x to get dh by dx, and then subtract fxt at the lower limit t equal to gx into the derivative of g with respect to x. So, this is a well known formula, the Lebanese rule. It is called Lebanese rule of differentiation under integral sign. Now, in particular, if gx and hx are constant functions, so then what will happen, the dh by dx and dg by dx will be equal to 0. So, this formula will then reduce to the derivative of integral gx to hx fxt dt with respect to x is equal to integral gx to hx partial derivative of fxt with respect to x into dt. Okay, so now we are going to discuss an important result. By using this result, we can convert a multiple integral into a single integral. So, you can see here that we have n integrals here, the limits of integration are x naught to x, and we are integrating a function of x which is by x. So, when you integrate by x n times with respect to x, what you do is you get 1 over n minus 1 factorial integral x naught to x minus t to the power n minus 1 by dt by t dt. So, the n integrals can be converted into a single integral. Now, here n is a positive integer and x naught is a constant. So, what you let us discuss the proof of this. Let us consider I n x equal to integral x naught to x minus t raised to the power n minus 1 by t dt. So, let us define I n x equal to integral x naught to x minus t raised to the power n minus 1 by t dt. Now, let us use Lebanese rule to differentiate this. So, by Lebanese rule, din over dx, let us differentiate it with respect to x. So, here lower limit is x naught which is constant, upper limit is a variable x. So, we are differentiating with respect to x. So, we get x naught to x partial derivative of x minus t raised to the power n minus 1 partial derivative with respect to x into by t dt plus the value of the integrand at the upper limit. So, we get x minus x raised to the power n minus 1 by x into derivative of the upper limit with respect to x minus the value of the integrand at the lower limit. So, x minus x naught raised to the power n minus 1 by at x naught into d over dx of x naught. Now, what we get is then when you differentiate x minus t raised to the power n minus 1 with respect to x partially, you get n minus 1 into x minus t raised to the power n minus 2. So, n minus 1 being a constant can be written outside, and we get x naught to x minus t raised to the power n minus 2 into by t dt. Now, here x minus x is 0. So, this is 0 into by x and dx by dx is 1. So, we get 0, and here we see that x naught is a constant. So, its derivative with respect to x is 0. So, these two terms vanish and we get n minus 1 x naught integral over x naught to x minus t raised to the power n minus 2 into y t dt. So, we can write it as n minus 1 times I n minus 1, where n is strictly greater than 1. Now, from this equation, from the equation I n x equal to integral x naught to x x minus t raised to power n minus 1 into by t dt. If we put n equal to 1, what we get? I1 x equal to integral x naught to x by t dt. So, if we again apply the Lebanese rule here, then we will get di1 by dx equal to integral x naught to x delta over partial derivative of by t with respect to x into dt plus by x into dx by dx minus by at x naught into dx naught over dx. Derivative of x with respect to x is 1, so we get yx here. Here y is a function of t only, so when you differentiate it with respect to x partially it is 0. So, what we get is 0 plus here we get yx, and here the derivative of x naught with respect to x is 0, so we get 0. So, we get yx here. So, when we differentiate I1 with respect to x, what we get is yx. Now, let us differentiate this equation din over dx again with respect to x. So, we will get d square in over dx square equal to n minus 1 din minus 1, and din minus 1 if you use it repeatedly, din minus 1 is n minus 2 in minus 2 and so on. So, when we differentiate it k minus 1 times, what we will get is k dk in over dx k equal to n minus 1 into n minus 2 into n minus k into in minus k, where n is greater than k. Now, in particular, if we put k equal to n minus 1 here, we put k equal to n minus 1 here, we will get dn minus 1 in over dxn minus 1 equal to n minus 1 factorial into I1. So, this is what we get when we put k equal to n minus 1. Now, if you differentiate this equation again, what you get is dn in over dxn equal to n minus 1 factorial into di1 over dx, and di1 over dx is by x. So, we will get nth derivative of in with respect to x as n minus 1 factorial into by x. Now, let us look at the equations 1, 3 and 4. If you look at equation 1 here, okay, when you put x equal to x naught, the limits of integration are same, lower and upper limit. So, at x equal to x naught in x is 0, and if you look at equation 3 here, if you look at equation 3 here, so this equation dk in over dx k, okay, is n minus 1 n minus 2 n minus k in minus k. In minus k will also be 0 by our notation. In minus k is integral x naught to x minus t raised to the power n minus k minus 1 by t dt. So, in minus k, and where n is greater than k, in minus k is also 0 at x equal to x naught. So, the dk in over dx k will be 0 when n is greater than k at x equal to x naught. This is 3, and then 4 here also I1 is 0 at x equal to x naught. So, dn minus 1 in over dxn minus 1 will be 0. So, from 1, 3 and 4 it follows that inx and its first n minus 1 derivatives when is at x equal to x naught. Now, so let us now go back to the equation di1 over dx. So, di1 over dx we can see when we integrate it with respect to x, we get I1 x equal to integral over x naught to x by t1 dt1. This is because at x equal to x naught I1 x is 0. So, we can also see it like this. We have di1 over dx equal to di1 over dx equal to yx. So, when we integrate over x naught to x, what we get is this, okay, and di1 over dx, when we integrate we get x1 x I1, so I1 x minus I1 x naught equal to integral x naught to x by x dx, but I1 at x naught is equal to 0. So, since I1 x naught is equal to 0, we get I1 x equal to integral x naught to x by x dx, which can also be written, since this is a definite integral, we can also write it as x naught to x by t1 dt1. So, I1 x is integral x naught to x by t1 dt1. Similarly, we can integrate similarly we can get I2 x equal to, because we see if we look at this, we have d square, let us put n equal to 2 here. So, we will get d2 I2 over dx2 equal to n minus 1 by x. So, when we integrate it twice, we will get I2, and integrating twice means when we integrate once we get I1 x, when we integrate again we get I2 x. So, I2 x equal to I x naught to x I1 T2 d2, which can be written as when you put the value of I1 T2 from here, you get x naught to x naught to T2 by T1 dt1 dt2. We can proceed in this manner and integrate it n times, integrate n times. So, we will get in x equal to n minus 1 factorial x naught to x naught to Tn, x naught to T3, x naught to T2 by T1 dt1 dt2 dtn. So, this is equal to 1 over n minus 1 factorial. In x we have assumed as x naught to x minus t raised to the power n minus 1 by t dt. So, this is how we prove that a multiple integral an integral of the function by x can be converted into a single integral. So, this result we shall be using when we deal with the initial value problems. So, this is what I have to say in this lecture. Thank you very much for your attention.